Let's summarize what we have learned in linear regression. We began with some examples of business problems, and we related those business problems to a problem space and a corresponding solution space, if you'd like to think of it that way. What this means is to identify from a business problem what is the response of a linear regression and what might be the explanatory variables. We then went and looked at correlation and linear relationships. The difference between correlation and regression is that correlation is something in which x and y are not distinguished. Correlation of x and y is equal to the correlation of y and x, which means correlation should not be confused with causation. A linear relationship, however, is going directly into the idea of using one variable to predict another. A simple linear regression is one variable being used to predict another using a straight line, which means an equation of the form y is equal to b0 plus b1 into x. The slope of that equation gives the effect of x on y. The idea of simple linear regression extends to multiple linear regression, where we can incorporate multiple independent variables, and the coefficients of those independent variables reflect the effect of that particular variable on the output. Y is equal to b0 plus b1 x1 plus b2 x2. b1 is the effect of x1 on y when x2 is kept fixed. All this made sense when we have numerical variables. So we can multiply and coefficients and variables like b1, x1, b1 into x1. But what happens if they're categorical variables? These are labels. So we need to convert a categorical variable on the explanatory side, on the x side, into numbers. And we can do that through various forms of encoding, from an ordinal variable, which are just converted into an integer scale, or for nominal variables, which are converted into dummy variables through a method called one-hot encoding, where if there are k categories, we end up with k one-hot encoded or dummy variables. We ended by looking at how one thinks of regression models as being good, and we looked at criteria like mean squared error, root mean squared error, mean absolute error, etc., that evaluated models from the perspective of how well they predicted. And we looked at R-square and adjusted R-square for trying to figure out how well the explanatory variables were capable of explaining and whether an added variable gave added predictions or not. At the end of our sessions on linear regression, you should now think about what we have accomplished and what you should be able to do going forward. You should be able to interpret a correlation coefficient, a number between -1 and 1, to explain the measure of strength and the direction of a linear relationship. Direction of a linear relationship means that if the slope of a linear regression is positive, that means that if the x goes up, then y goes up. If it is negative, it means that the x goes up, y goes down. So this idea of a positive and negative relationship understood through a regression and understood through a correlation measure. This should allow you to construct and interpret simple linear regression models, extend that interpretation to multiple linear regression models. In a multiple linear regression model, each variable gets a coefficient, which can be interpreted as the change in the output that is caused by the change in that input, provided everything else is the same. An alternative way of using a multiple linear regression is simply to take all the x's and just to predict the y, and not worry about which x is doing most of the heavy lifting. So you can enable a prediction as well. These, remember, are the two main purposes of linear regression: being able to understand which x is important and being able to predict the y. Both of these criteria are put into play when you are evaluating business linear regression models through criteria such that root mean square error, which is an expression of how good the prediction is, or a criteria like adjusted R-square, which is a measure of how well the variables are explaining the output. But of course, the most important learning outcome and the most valuable thing that can emerge out of these sessions is your ability to identify a business problem as an application of linear regression. To say, this is my Y and these can be my corresponding X's. To deal with the data challenges that come correspondingly, and to be able to run a linear regression. To use it to either predict or to be able to explain variables. And for that, you might need some practice on how regression models are built so that you will be able to meet both of these objectives and figure out any particular data nuances like categorical variables you will need to deal with. So at the end, I leave you with the message that linear regression is one of the most powerful tools in the arsenal of those who build models to predict outcomes. It is also a basic technology around which other machine learning algorithms and other more advanced AI technologies are built. And those learnings will come in other sessions. And so, happy learning as you use this in practice and as a basis for other very interesting algorithms that are going to come in the future.